Hello, this is the next video in a playlist that I'm calling Hypothesis Testing, and here we're in a little mini series within that playlist. And the mini series deals with two-sided, uniformly most powerful tests in the one-parameter exponential family. And here we're going to look at testing the variance of a normal distribution. And the null hypothesis is that is it less than some value or greater than some value, and the alternative hypothesis is it between the true variance between those two values. The must watch is parts 1 and 3. Part 1 deals with the theorem that we're going to use, which is an extension of the Neyman-Pearson lemma, which is kind of cool in itself. And part 3 deals with more some of the theory behind this R illustration. And so let's just jump right in. And so our null and alternative hypothesis is this. We're going to use 3 and 8. So the null hypothesis is the true variance less than or equal to 3, or is it greater than or equal to 8, or is it somewhere between 3 and 8? And that's the alternative. So let's load S1 and S2. That really stands for sigma 1 squared and sigma 2 squared. We're going to use a known mean of 22, but it's really irrelevant in this example. Initially, we're going to have a sample size of 25. We're going to use an alpha of 0.05. And here we create xd1 and xda, and those are pairs. So xd1 picks values along the chi-square distribution, and then xd1a pairs that value with the value in the chi-square such the area under the curve is alpha. So those two are paired. And then from that, we pick all possible C1 and C2 values given those both situations. And so the plot of what we just calculated is this. So this black line are possible C1 values based upon that condition, and the red line is possible C1 and C2 values based on the second condition. Note that the curves are almost identical, but one is stretched out. And the reason for that is the black line is using sigma 1 squared, which is 3, and the red line is using sigma 2 squared, which is 8. So it stretches all the possible values. But really, we're trying to find that intersection right there, the C1 and C2 that are equal. And that's what this R illustration is trying to find, that exact dot, that point. So what we do is we create a function. And so let me go back here. So once we pick a C1, then we create a function to calculate the C2 value and a function to calculate the C2 value in this red curve. And essentially, for a C1 value, we want to find the C2 that makes, the C1 that makes the C2 values equal. And that's what we're trying to do. And so we create this function where, these are the C2 values given the C1 values, and, assuming sigma 1 squared is true, and this is the C2 values given that the sigma 2 squared is true, and we want them to equal. So then we use uniroot and cycle through all the possible values to find the C1 that's true, and then from that we calculate C2, and this is it. So it's 109 and 127, and if we look back at this graph, so that's 109 and 127. Is that what I said? And that's it. I mean, that is so cool. And that's it. That's the critical region for this uniformly most powerful test. From that, we can calculate the power curve. And this is cycling through all possible sigma squared values. And notice here, our null hypothesis is less than 3 or greater than 8. And notice that the size of the test is definitely less than alpha, which is 0.05. The power goes up in the alternative region, which is kind of cool in itself. So the power is around 20%, around 4.5. So that's it. So to do a computer simulation with 300,000 replications, This is it. We create a matrix with 300,000 rows and columns and in columns. And so the number, each row represents a sample of size n. And so we store our values in there, and then we take the row sums for each row, and then we see if it falls in the rejection region or not. And let's look at the tables, and notice 15,000 of them fell into the rejection region, which is roughly about 0.05, which is it should be. That's on a boundary point. And if we do this for 8, that's also a boundary point of the critical region, should be around 0.5, and it is. And we said that a value of 4, 4.5 was the, I forgot what, 0.2. Yep, and that's it, 0.17. And so you can see that that's true, because 4 is, probably here. Oh, it's in between, which is 0.17. Yep. Now, one thing I did not illustrate in the previous example is that I tried to write it to make it, you could change these up. Let's change this to 4, and let's double our sample size to 50 and rerun. And in this program, you can change the alpha value if you want. You can change the mean value if you want. So let's run it and see what we get. First of all, let's look at the plot that we're trying to solve, which is not necessary, but I think is pretty cool. So we're trying to find that dot right there. So let's call it 270, and I don't know, whatever that is. So let's see what they are. So now we run it through our function here, and we get 262 and 292. Those are the critical values for the uniformly most powerful test. If we were to do a power curve for this example, it would look like this. This is the power curve. And if we were to do simulations, it would also come up with consistent results. So notice that we changed the boundary point to a square root of a variance of 4, and we got 0.05, rounding. So it's all accurate. So anyway, that's all I have for this video. As always, I'll copy and paste the code into the comments section if you want to copy and paste it into your R program. Hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.